Welcome to iLecture Online, and here we're going to talk about another property in optics called refraction. And what refraction means is that when a ray of light moves from one medium to another medium, for example from air to glass, something happens once it crosses that boundary. The reason why something happens is that there's some property about glass that does something to the speed of light as it travels through it. It actually slows light down. So if we know that the speed of light right here is equal to c when light is traveling in the air, what is the speed of light equal to once it traverses into glass? Well, that depends on something called the index of refraction. So let's write that down, index of refraction. And to indicate what that is, we use the letter n. So we use the letter small n to indicate the index of refraction. And since I like to denote when a ray travels from one medium to another as going from medium 1 to medium 2, I'll call this n1 the index of refraction of the first medium, meaning air, and n2 is going to be the index of refraction of glass. Now for air, the index of refraction happens to be 1, and for any other substance it tends to be more than 1. So for glass it's typically maybe like a 1.5 or 1.6, so let's call it 1.6. Okay, then what does that mean as far as the travel of light through these two mediums? Well, if the velocity of light is c when it travels through air, then for the velocity once it travels in the glass is equal to c divided by the index of refraction. So in this case, we know that c is 3 times 10 to the 8 meters per second, and then we divide that by 1.6, and that will give us then the new velocity of light. And I just remembered, I did not bring my calculator, so let me get my calculator real quick, and I'll be right back. Now that I have my calculator, let's find out how fast light travels through glass. Well, for glass that has an index of refraction of 1.6, so we take 3 divided by 1.6, and we get 1.875, so this is equal to, and let me go like this, equal to 1.875 times 10 to the 8 meters per second. So a significant slowdown, still fast, but you can see that light does travel at a different speed once it enters a medium other than air or just free space. So what happens now when a ray of light travels from one medium to another? And here we have air and water, doesn't matter, just two different mediums. And the index of refraction for air, n1 equals 1, for water, n2 equals 1.33. Now notice that the light does not travel straight across the boundary at a line that's perpendicular or normal to the surface. It travels at an angle relative to the normal. And when it crosses a boundary like that, something else happens to the light besides it slowing down. It also changes direction. It bends or it refracts, as we call it. And in the case of light that travels from an index of refraction which is smaller to an index of refraction which is larger, the bending will be what we call towards the normal. So the angle between the normal and the ray will become smaller, and so the light will do something like this. And this will now be theta sub 2. Notice that theta sub 2 is indeed smaller than theta sub 1. Well, how do we actually find out what those angles are? Let's do a quick example. Let's say, for example, that theta 1 is equal to 30 degrees. Then what do you think theta 2 will be equal to? Well, it turns out that Snell's law enables us to do that. And Snell's law says that n1 times the sine of theta 1 equals n2 times the sine of theta sub 2. And again, what we're trying to find is we're trying to find the angle sine of theta sub 2, which means we have to algebraically solve for that angle. So we're first going to flip the equation around. So we could say that n2 times the sine of theta 2 equals n1 times the sine of theta sub 1. Then the next step is we're going to divide both sides by n sub 2, so we have the sine of theta sub 2 is equal to n1 over n2 times the sine of theta sub 1. And finally, to find theta sub 2, we take the arc sine, so theta sub 2 equals the inverse or arc sine of this whole thing right here, which is n1 over n2 times the sine of theta sub 1. Now plugging in the values that we have, so we know that theta sub 1 is 30, n1 is 1, and n2 is 1.33. In this particular case, because it's from air into water, we can say that theta sub 2 is equal to the arc sine of n1, which is 1, and 2, which is 1.33, and times the sine of 30 degrees. Okay, let's find out what that's equal to. So take the sine of 30, that should be 0.5, divide that by 1.33, and then take the arc sine of that, and we get 22.1 degrees. So theta sub 2 is equal to 22.1 degrees, and that's what we call the angle of refraction. Let's write that down. So that's called the angle of refraction. Okay, so notice that when the angle is 90 degrees, or I should say 0 degrees between the normal and the ray, there's no bending of light. The light goes straight through. The only thing that happens is that it slows down relative to the index of refraction. In this case, let me just put down v sub 2, and that's the velocity in the second region is dependent upon the index of refraction in the second region. But if the ray comes in at an angle, then not only does it slow down once it crosses the boundary, it also changes direction. It has a new direction. The angle of refraction is different from the angle of incidence, and using Snell's law is how we find what that angle is. All right, so there's a nice little introduction to the concept of refraction.